Here we have a rectangle inscribed in a semicircle of radius 2. We need to find the largest area of the rectangle that is inscribed inside this semicircle, and we need to find what the dimensions are. So we've already started to sketch here on the XY coordinate system. We have the circle centered at the origin, and so you see we started on the x-axis from -2 to +2. And then that we recognize that that equation for the semicircle is x squared plus y squared equals 4. And but it's only in the upper hemisphere. Then we inscribe the rectangle approximately. We inscribe it inside. It's going to have the x coordinates, -x and +x there. And we see that for on the right side, we have the diagonal from the origin out to the circle has a measurement of 2 because that is indeed the radius of this circle of radius 2. That's where that 2 came from. So the ordered pair that we have in the right upper corner for the rectangle's intersection with the semicircle is the ordered pair xy equals x comma the square root of 4 minus x squared. And you'll see where that comes from, the y coordinate. That comes from just solving the equation of the circle for y and only retaining the positive root in the upper hemisphere. Okay, let's do our steps. Step 1, we're going to maximize the area of the rectangle. That's what we were asked to do. Maximize the area of the rectangle. All right, so that would be the formula A equals 2x times y. Why 2x? Because look at the rectangle. The bottom side and the top side, they have x plus x distance, so it's 2x for that distance, and then the height is y. All right, but we need to get rid of the y, so we're going to use the equation of the circle. Solve for y, we get y equals positive square root of x minus 4 minus x squared, and we only retain the positive root because we're in the upper hemisphere where the y's are always positive. So a equals 2x times the square root of 4 minus x squared, and that is step 2 where we relate the a to one variable. Now let's take the derivative and find the critical numbers. A prime of x turns out to be a mess, yes, because we have to use a chain rule. We have to use a chain rule, we have to use a product rule, and we finally end up with negative 2x squared over the square root of 4 minus x squared plus 2 times the square root of 4 minus x squared, where the domain x is in the domain between 0 and 2. In other words, x is going to be in the first quadrant. And you can just see that by the sketch. Okay, so for the critical numbers, we're going to set the derivative equal to 0 and solve for x. That gives us negative 2x squared plus 2 times 4 minus x squared equal to 0. And that ends up giving us x equals plus or minus the square root of 2. I'll let you catch up right here. So we set the whole derivative equal to 0. And then we get a common denominator that's not shown, and then we just set the numerator equal to 0, and we solve that for x. X equals plus or minus the square root of 2. Okay, step 4. Let's use note 70 on a closed interval. First we'll evaluate the a at the critical numbers. A of the square root of 2 is equal to 2 times the square root of 2 times the square root of 4 minus 2, which is equal to 4. And we ignore a of the negative square root of 2 because x equals negative square root of 2 is not even in the domain from 0 to 2. I'll say that in this line. Ignore a of the function a evaluated at x equals negative 2 because that value for x is not in the domain of a, which was between 0 and 2. That was our restriction because we're only interested in that right side right now. Evaluate a evaluated at the endpoints, a of 0 and a of 2. They both give you 0. So by note 70, the closed interval test, we see the area is maximized when x equals the largest value, when the y value is 4. So that means when x is the square root of 2, its max value is 4. That will be our maximum area. Then step 5 is where we draw our conclusion. The dimensions are going to be x equals the square root of 2 and y equals the square root of 4 minus the square root of 2 squared. So that's 4 minus 2 under the big radical sign, which turns out to be the square root of 2. Thus, we have these dimensions on our rectangle that's inscribed in the semicircle. The length is the square root of 2. The width is 2 times x, which is 2 times the square root of 2. As you're finishing this up, I just want you to note that our positive x value could only live in the first quadrant because of the way we sketched it. And that's why for the closed interval test in step 4, where we used note 70, we chose the closed interval from 0 to 2. That would be x equals 0 to x equals 2, which would give us the first quadrant.